We'll go from current slide. But let me make this announcement first. Now, seems like when I did this tech class, either everybody or almost everybody's been coming, I would say it this way, I think. Maybe not, I don't know. I think has paid, but for people who haven't completed payment, if that includes any of you yet, please get that cleared up, because at some point, and I don't know, they never tell us when, just at some point they decided to remove all unpaid students from the roll. Okay? And then you can usually argue your way back in. So it's much better to get it done now rather than waste all the time that it takes to do that. So I just wanted to say that. And then the second thing is, I don't know if any of you are at all ever would think of coming in on a Tuesday or a Thursday when I have more office hours than I do on Monday and Wednesday. Monday and Wednesday I have 30 minutes in the morning and 30 minutes in the evening right after this class. And that's all. I got 5 minutes in between classes otherwise, and like you just saw, I can't get anything done in those 5 minutes. So, just notice I left one blank here. Okay. But if you were thinking of coming in tomorrow to see me for any reason whatsoever, don't. Okay? I've got eye surgery tomorrow. I have to have a cataract removed and a lens put in its place. I've had this one done more than 9 years ago, so it's not a big deal, except it takes, well, I have to be there at 5:30 tomorrow morning at the hospital, Foundation Hospital, and then I'm in line and procedures, and they come through and do all sorts of mess for most of the morning, and then finally I'll get around to doing the surgery, and then they'll send me home. But I'm not supposed to do anything, and probably won't be able to read much or anything, because this eye will be completely covered, and this eye is a distance eye. It's really hard to read from this, because the lens in this is a distance lens. The one they're going to put in here is a near vision lens, so I'll be able to go that way. But as long as that eye's covered, it's going to be hard to read anything. And they don't want you driving or anything else, at least that first day. So I won't be back on campus at all tomorrow. Okay? Now, next Monday, should be here, should be no sweat. You probably won't be able to tell a thing. Okay? Except I might not have to get as close to the page to read. All right. Any questions before we get going today? All right. Where we left off last time, we were doing example 5, and I think we got almost all of 5 done, except right at the bottom of the page, on page 850. And let's see if I can find the place where we were. Okay. Wow. Didn't know we were that near that there weren't any other things here. Now, this is unfortunate. Okay. What I'm going to do, when we did it in class, we didn't do it the way they did here. Certainly this is doable. To get the normal component of the acceleration vector, they do v cross a, which is not hard to do, and magnitude of v we'd already done, but then they're going to do the magnitude of v cross a, which still isn't a very hard thing to do, but it was really an easier way to go about it. So this is certainly one way to get it, but I need some room to write on. So what I think I'm going to do is scroll back up here. Whoops, too much. Okay. Yeah, this will be everything that we need. Here's the alternative way to doing the normal component. Here's the tangential component of the acceleration, and we did that last time. Hopefully you remember that, right? And this is strictly, these components are scalar quantities. They're not vectors. They're components of a vector, but they go with the unit vector, unit tangent vector. This one does, and the other with the unit normal vector. Okay. Now, what you can't see here, but it's really on the page here, is the acceleration vector is equal to 2k. Now, we had that from before. In fact, I'll go back and show it to you. Right there, acceleration vector is equal to 2k. We did that last time. Okay? So, with that in mind, we have the unit tangent vector there, the total acceleration vector here, what the normal component of the acceleration vector. The easy way usually to calculate this is to do the square root of a squared, the magnitude of your acceleration vector squared, minus this a sub t, which is 4t over the square root of 10 plus 4t squared. Okay, but that's squared because you're doing a square root. Okay, so that's the difference of their squares. Okay, now the reason for that is the acceleration vectors here, if this is a normal component, then that's the tangential component. If this is the tangential normal component here, it's got to be the difference of those squares because that forms a right triangle. Okay? And what this is your tangential component, okay, in the direction of the unit tangent direction. And here's this. So this is a piece of cake. What's that squared? Magnitude squared? 4, right? Because this is magnitude 2. Okay? Square that, and you got 4. So this would be the square root of 4 minus, now when you square this, this gives you a 16t squared in the numerator, and in the denominator you just get what's under the square root. 10 plus 4t squared. Alright, now, the rest of it's just sort of algebra. It's the square root of, to get this under the same denominators, let's multiply this by 10 plus 4t squared, and multiply that by 10, I can't write, plus 4t squared. Okay? So what that gives you in the numerator here is 40 plus 16t squared minus 16t squared, look, oh joy, those go away, divided by 10 plus 4t squared. Okay? Now, you can factor out a 4, which is a perfect square, so this would be 2 times root 10 over 10 plus 4t squared. Okay? Now, hopefully that's what they got. Yeah. 2 times the square root of 10 over square root of 10 plus 4t squared. Exactly. Now, it happened to be that this V cross A that they use to calculate is a really easy thing to do. So in this case, their way of doing it, and there it is right here, is this V cross A. The magnitude of that would be the square root of 4 plus 36. That's your square root of 40. So that comes out real easily over the magnitude of this, and there that was 10 plus. So yeah, you get that same thing really easily here because that wasn't a hard calculation to do. But you still had to do it. This way you didn't have, you could stop right up there and get everything done from there. So it's pay your money and take your choice. They're both easy. Most of the time, this technique is easier. That, where we got, yeah, this one right here. Once you have the acceleration vector, you had to take the magnitude of it. You already had the, this one you just calculated. Take the, square it, okay? And then take the difference of those. The rest is just pretty much algebra, and it came out pretty clearly. In this particular problem, this wasn't a hard calculation to make. Sometimes they are a lot harder than that, but it came out pretty easily, so that came out pretty nicely too. So either way worked, you got the same answer. Hard to see here. Let me erase at least part of this. No, that's my answer. I didn't want to erase it, but I guess I've got to. So let's just erase it all. Just remember it's 2 root 10 over 10 plus 4t squared. And there's your root 40 in the numerator, and that's 2 root 10 over square root of 10 plus 4t squared. So both of those are pretty easy to calculate. Usually this can be a lot harder to do than the other technique I just showed. All right, now that would finish the slide set, except we have at least 2 more examples to go. So let's back off. Goodness, can't I get more white space than that? Yeah, there we go. Okay. Here's a circular helix. We didn't do this one last time, did we? I know we did some circular helixes, but I don't think we did this one. Find the tangential and normal components of the acceleration for the helix given by r of t is equal to b cosine t a. I don't know where I got an a from. Plus b sine t j plus CTK. Okay, and this is good for all b's greater than 0. Okay. Now, missing a few numbers here, aren't we? Not a single digit in the problem. Okay. But this describes b cosine ti plus b sine tj. That describes a circle of radius b. So I just as soon call this r. Well, except they already have this r. So radius better than that. CT is just the rate at which it's climbing up the thing. So a circular helix is picture a spring like a slinky that you've evenly done, and that's the path that you've got going here. Okay? Radius b. Now, it says find the tangential and normal components of the acceleration for that. The helix, the helix isn't going anywhere. The object is going on the path of the helix. Okay? So what is one of the first things you got to do? Pretty obvious. Take a derivative. Good deal. R prime of t, which by the way is v of t. Okay? And what would that be? Negative b times the sine of t, I, plus b times the cosine of tj. Help me? Plus what? CK, because the derivative of CT is just C. Okay? That'll come back, I hope. Okay, there it is. All right. There's your velocity vector, which is R prime. What else do we need? Now, just to refresh our memories, let me scroll back. Oops. Ha! Right here. What do we need? The tangential component. We need the magnitude of that velocity vector. unit tangent vector, or velocity and acceleration and the magnitude of this. This, I think, is the easiest thing to get. We've already got velocity, fairly easy to get this, and one step to get that. Okay? So what you want to do next? Either magnitude of magnitude of V, or acceleration. They're both straightforward from what we got here. Which one you want to do? Got to do them both. Magnitude first. So let's do the magnitude of your velocity vector. And what would that be? I know it's going to be a square root. What's going to go in there? Okay. B squared sine squared theta. Sine squared t, sorry. Plus B squared cosine squared t. Plus C squared. By that, see why? Square root of the square of their magnitudes, of their components. What do you notice about these two? The sine squared t plus cosine squared t is 1. They've got a common factor, b squared. Factor out the b squared, and you get 1. So this is just the square root of b squared plus c squared. Oh, wow. Okay. That's the magnitude of v, your velocity vector. Next. What's the other thing we needed? The acceleration vector. And what is the acceleration vector? It's the first derivative of the velocity vector, which is the second derivative of the displacement vector. And what would that be? Get out of there. Minus b cosine ti minus b sine tj, and that's all, folks, right? That's it. The derivative of c is 0. All right. All right. We are now ready to do your acceleration, the tangential component of the acceleration vector. V dot A divided by magnitude of V. Pretty straightforward, fairly easy to do. We just got to do V dot A first. Do you remember what V dot A is? Yeah, you do the product of the similar components, add them together. It's a scalar quantity. It won't be a vector. Okay? So this will be what? Multiply those two together, and what do you get? The I components together. What do you get? V squared sine t cosine t. No i's or j's in it. They're not vectors anymore. And then what you get here? Minus b squared sine t cosine t. Whoops! What does that give us? 0. Okay, the dot product is 0. This may be a problem, or would it? Meaning there is no, let's phrase this properly. This is to get the tangential component of the acceleration. Okay? Kevin's here. All right. Anyone else come in since the call roll? We've had someone leave, but no one else come in. All right, what does this mean? The tangential component of the acceleration is basically going back to this, right here, the change of your speed. The magnitude of your velocity vector is your speed time rate of change of that speed is 0, meaning it's going at a constant tangential velocity. The normal acceleration may be changing like crazy, but tangentially, the speed is staying constant. The speed is constant. That's what it's telling. So all of your acceleration vector is going to be your normal vector. Okay? So that makes it a very easy thing to do. So your A sub t is equal to 0. That makes your A sub n exactly what your A is. It is that. It is how do you say that? Well, it's basically the magnitude of that, okay? It's the square root of, this don't seem crazy, but it's absolutely correct, the square root of b squared cosine squared t plus b squared sine squared t. Okay. I don't know why my pen is flaking in and out on me. So, and what does this come out being? B. Because cosine squared plus sine squared is 1. 1 times b squared is b squared. Square root of b squared is b. Okay. That's it. Normal component is b. Now, and that's a constant. Okay? I don't know. Not much else we can say about this. Tangential component 0, normal component b. Any questions? Looked like it might be a tough problem, turned out being the simplest one we've done. Okay? All right, to erase. All right, projectile motion, example 7. The position vector for a projectile shown in 1227, and I know not everybody has a book, and certainly people at home aren't going to be able to see this anyway, but I'm going to hold it up here. Here's your figure 1027. There's your projectile motion. You're moving along like that. It's not really clear. Yeah, it does look like this may be parabolic. You may have things that are not parabolic motions if you have air resistance or other things like that taken into account. This does seem like it's part of a parabola, so we'll leave that alone like that. The position vector for the projectile shown in figure 1227 is this position vector. R of t is equal to 50 root 2 times t. Now, I really don't like them writing it that way. I'd rather say 50t times root 2 or something like that, just so you don't think that the t is under the house, under the radical. The way they got it written in the book, you could make that mistake unless you're very carefully watching. Okay? Plus 50 root 2 t. Again, that t is outside the radical, so I'll really move it over. They don't necessarily. Minus 16 t squared j. Okay, this is just two-dimensional motion, and the figures show two-dimensional motion. And this is regular motion. I'll tell you what I can tell you now. The initial velocity of this was 100, whatever units you're using. Why? Because these two components are exactly the same. So it has to be 45. 45 or pi fourths. That would be square root of 2 over 2 times whatever the magnitude was. This is your square root of 2 divided by 2. 100 divided by 2 is 50. So this was initial velocity of 100 meters per second, feet per second, whatever the units were. Feet per second, I will say. The reason I say that is your acceleration is minus 16, that's 1/2 mile. Minus 1/2 gt squared. Well, g would be 32 if this is 1/2 of g. Well, that's the acceleration due to gravity in U.S. customary feet per second. So this would be 100 feet per second, initial velocity at 45 degrees, of those two are the same, and that would be acceleration due to gravity, 32 downward. Okay? Now, you don't need to know all that, but looking at it, really you can tell that. Find the tangential components of the acceleration when t is equal to 0, 1, and 25 root 2 over 16, one of my favorite numbers of all time, when t is equal to that amount. Find the tangential components of the acceleration. Okay? So what must you do first? Well, someone piped in really well last time. Take a derivative, of course, r prime of t, which is going to be your v of t, okay, is equal to what? Help me. Anybody? Pretty exciting, huh? Second, take a derivative of that. If that was 7t, what would be the derivative? 7. So this is just, oh, I'm sorry, I can't hear. Okay, 50, I can't see, I can't hear. I'm worthless, okay? 50 root 2i. Next. $50 root 2 minus 32t j. Got it. There's your velocity vector. Okay? All right. Now, remembering from before, let's go back one. What it is, VIA over magnitude of V. So we need an A and we need a magnitude of V. Which one you want to do first? Do the A first. What is A? A of t is the first derivative of the velocity of with respect to time. I can't write. Which is the second derivative of your displacement with respect to time. Okay? And that will be what? A little louder. Negative 32j. And we had already known that because we said the acceleration is due to gravity. This must be the U.S. customary system minus 32 feet per second squared. Yeah, okay? We'd already surmised that. Okay. Now, what we have is the tangential components of the acceleration when t is equal to 0, 1, and this other number, 25 root 2 over 16. Okay? Now, they're only asking for a tangential, so what was that? A sub t. I'm sorry, capital T. Remember what it was? Yeah, V dot A over magnitude of V. So we still got to do magnitude of V. Let's do that first. The magnitude of V help me, somebody. Okay, magnitude is going to be a square root. I'll do that part. What goes in there after that? Square this. That would be 2,500 times 2, which is 5,000. Right? Okay. Plus, it's going to be another 5,000. Okay. Because that's what you get when you square this part. Then you got twice the product here, which would be 160 root 2 t. No, minus 160 root 2 t. Did I double that? No, I don't think I did I? Double it is 320. Okay, sorry. Could have done it much easier. Okay, think of it this way. It's twice the product of these two. Well, twice this is 100. That's easy. And 100 times minus 32 is minus 320. Whoop, I need another 0, don't I? Times root 2. So 3,200 times root 2. Okay, glad I went back to explain that. And then we have a plus. Someone's going to have to help me with what 32 squared is. 1024? Is that right? 1024 t squared. All right. Whoa. Let's do what we can with that. It's the square root of 1,000, 10,000, minus 3,200 root 2 t plus 1024 t squared. Okay. Now I'm sure something will factor out of that. I'm not sure anything very useful will factor out of it, but something will factor out. In fact, I know something will. I know 4 belongs here and here and here. Anything bigger, 16. 16 going to 10,000, I don't remember. You will? An even number of times? Okay, well, how many? 625. 625? Is that what you said? Okay, 625. So that's the biggest. So I think we can pull a 16 out, which is a 4 on the outside, which would be a 4 times the square root of, and you said that was 625 left? 625 minus, and 16 will go in that 200 times, root 2 t plus, I know 16 will go into that, is it 16 times t squared? Okay, I don't think there's any other perfect square factors that'll pull out of All right, so there's your magnitude of your velocity vector at any time t. I'm sorry. So what we've got to do next is do our dot product. The dot product of v of t dot a of t. The i's, there is none because this is a 0, so it's 32 dotted with that, multiplied by that. Well, 32 times 50 second 1600 root 2 minus 1020 or plus 1024 t. Okay, I believe that's right. So that's okay, and that's divided by the magnitude of this, which is 4 times the square root of 625 minus 200 root 2 t plus 16 t squared. What a mess. Okay? Let's see if anything comes out of that. That's your tangential acceleration of the vector. Okay? Component of your acceleration. Okay? So when t is equal to 0, I think I can almost do this. When t is equal to 0, this one's 0, and those two are 0, and you have minus 1600 root 2. Our writing stinks. Times divided by or over 4 times the square root of 625. The rest go away. Now, is 625 a perfect square? I believe it is. It's the square of 25, isn't it? Yeah, okay. So that would be 100 in the denominator. That wipes out the 2 zeros up there, and that would give us minus 16 root 2. That's at t is equal to 0. Let's see, minus 16 root 2, approximately minus 22.6. All right? That was easy because the 0 was easy to substitute. This is at 0. A, the tangential component of this at, what was it, 1? Okay. This will be a minus 1600 root 2 plus 1024 divided by 4 times the square root of 625 Boy, it would help if I could read my writing. Minus 200 root 2 plus 16. Because when t is equal to 1, those all go away. Now, they factored out a lot more than I did, but anyway, what do you get when you do all that? Wow, what a pain. It's a lot of agony to just punch in those numbers, they get, if I did the numbers right, approximately negative 15.4. No nice, easy, round numbers to do. Okay? Now, the next one should come up much easier, though it looks like it would be a pain in the neck. That's when t is equal to, thought I wrote it down somewhere, but I don't see it. A, the tangential component of your acceleration vector when t is equal to 25 root 2 over 16. Okay? It seems like that's going to be a real bear, but let's see what it is. Minus 1600 root 2 plus 1024 times 25 root 2 over 16 okay, running out of room. All that's divided by 4 times the square root of 625 minus I really don't want to write all that down, and I'm not going to, because I've looked ahead to see what the answer is. Let's do this first. Okay? $25 times that, whatever it comes out being, you're going to divide by 16. 16 will go into that 16 times. So 16 times 25 is 400. That's 400 root 2. Yeah. Seems like I've dropped a number somewhere. I can't see where it is. Okay. Anyway, in the book you see it comes out 0. Because the numerator and it subtracts off and becomes 0. That's why I quit writing the denominator, because I knew that was supposed to be 0, but I don't see how it becomes 0 now. Okay. So I must have gotten something wrong up here. But anyway, it comes out 0. Here's how we know. Okay? Because that is a parabolic path, and at that time there, your acceleration is all down. Okay? You're no longer going up, you're like this. Okay? And your acceleration is all down, so there is no tangential component of the acceleration at all. So that is indeed 0. See, going up like that, it's the negative component of acceleration. Down like that, it's the positive acceleration. Here, it's 0. Now, so many places to have slipped up and made an error there. I'm not about to try to chase them down right now. Okay. That does finish 12.4. Homework exercises here. Do any of the odds 3 through 7. They're all at Calc Chat. 5's at Calc View. Any of the odds 9 through 13. They're all at Calc Chat. 9's at Calc View. Any of the odds 15 through 19, they're all at Calc Chat. 15's at Calc View. Either 21 or 23, they're both at Calc Chat. Any of the odds 25 to 29, they're all at Calc Chat. 27's at Calc View. Either 31 or 33, they're both at Calc Chat. Any of the odds 35 to 39, they're all at Calc Chat. 35's at Calc View. Okay. Any of the odds, I think you can do 41. It should be at Calc Chat. 43 should be at Calc Chat. 45 should be at Calc Chat. Boy, my eyes are giving me fits. I need another drop in them. Any of the odds 47 to 51, they should be at Calc Chat. 53 or 55, they should be at Calc Chat. Let me see. I would say either 57 or 59, they should be at Calc Chat. 61's sort of an interesting one. Air traffic control, that should be at Calc Chat. 63 should be at Calc Chat. Either 65 or 67, both should be at Calc Chat. True false 69 should be at Calc Chat. 71 should be at Calc Chat, and 73 and 75 are proofs. If you choose or want to do those, knock yourself out. Goodness, my eyes are hurting. Okay. So let's move on from there. Goodness gracious. All right, that finished. That finished 12.4. Let's move on to 12.5, which is the last section in the chapter. Okay. Wow. I don't know why they just sort of started there. I shouldn't be rubbing them, but okay. Let's start from current slide. All right, chapter 12, still vector value functions. 12.5 is arc length and curvature. What the objectives here are: find the arc length of the space curve. Now you'll find some pretty similar procedure to what we did with arc length of a plane curve. Okay, at least it'll look fairly familiar. We'll use the arc length parameter, which is a sort of a nebulous little quantity, sorry, to describe a plane curve or space curve. That does a real good job of that. The trouble is they're hard to know what they are. We'll find the curvature of a curve at a point on the curve, plenty of curves in that sentence, and then we'll use a vector value function to find frictional force. That seems like that fits the others really well, doesn't it? All right, so let's do arc length. If you go back to 10.3, you can see the arc length of a smooth plane curve, and that's given by, not given here at all, okay? Let me write it down for you. Let me get my pen set up. The arc length is equal to, from A to B, arc length between, and your whatever your parametric, your parameter is, t, is going from A to B, and the arc cut by that is the square root of x prime squared plus y prime squared. This is two-dimensional, so that's all you got here. Okay, times dt. Not that bad of a formula, okay? Pretty straightforward. I don't know if you know or even care where that came from, but if you went back to the arc length of not a parametric function, vector function, but just the other, it was somewhat similar to the square root of 1 plus dy dx squared dt. And this is not too far from it. It's just that you have an x component and a y component. Dx dt is different from dx dx. That's why it was a 1 there. So this is a simpler formula. Okay? And because of that, the arc length here is just a direct link to that. And if C is a smooth, the formula for the arc length of the plane curve has a natural extension of the smooth curve in space, stated here. If C is a smooth curve, now what do we mean by smooth curves? No corners, no cusps, okay? Things that are derivative, that all the derivatives exist everywhere, okay? So smooth curve given by R of t is equal to x of ti plus y of tj z of tk. All these are differentiable at least twice, I believe. At least once, I know, but maybe even twice on an interval a to b. Then the arc length of that from a to b, and this is the symbol they use for arc length, s, the integral from a to b of the square root, just the exact extension before, x prime squared plus y prime squared plus z prime squared dt. Which, if you look at that, that's just the integral from a to b of your first derivative, which is also your velocity vector squared. Okay, if t stands for time, then that would just be, the magnitude of velocity vector, or the r prime. Okay? Now, that kind of makes sense, doesn't it? That if you're moving along a curve at a certain speed, multiplying the speed times time, if this is indeed velocity, magnitude being speed, speed times time is distance. So that would represent the speed times the time incrementally done from A to B. That should be the entire arc length. So that's one way to sort of remember that, okay? And it's a very straightforward, useful, hopefully familiar formula, okay? Now, let's do example 1. Find the arc length of the curve given by r of t is ti plus 4/3 t to the 3/2 power j plus 1/2 t squared k. Yeah, same as here. From t equals 0 to t equal 2. Okay, now this is a three-dimensional graph, and I'm so glad they drew it because I hate drawing those things. And even with their drawing, it's kind of hard to see what's going on here. And let's just think about it a minute. And this is from t equal 1 to 2. T is equal to, 0 to 2. T is equal to 0, you're at the origin, obviously. 0, 0, 0. Okay, you're at the origin. T is equal to 1, you're 1 on I, 4/3 on j, that would be about here, and then 1/2 on k. Now, so you're here, something about here and there. So that looks relatively close to reasonable, okay? When t is equal to 2, you've moved to 2i, and then what in the world is the square root of 2 cubed, some number, 2 times 1.414, whatever that is, but 4/3 of that. So you've gone quite a ways on J here, okay, and then you've gone up 2 units on K. So let's see, 1, 2, yeah, that looks about right. So here's your I component here, J component right there, something along in there, and then up to there. So it's coming out and curving around like that. Still getting further from the origin, moving faster along J than it is on I, but still coming out and moving up. Ultimately, it'll be faster on K. Okay? Not yet, perhaps. Okay. So, we want to know what the arc length is. There's the curve. What would be the arc length? What's the first thing you're going to do? Well, any way you want to do it. What is the arc length? Symbol is S. All right. It's an integral, so we are going to integrate out the t. What is that S? Integral of what? And from where to where? T is equal to Z. My throat's going on me. T is equal to 0, the t is equal to 2. So obviously you have a dt in here. What goes in here? Square root, for sure. All right. Here is Rachel, right? Okay. Missing Carlton, Nolan. That's all that's been here. Okay. So what goes first thing under the square root? 1. Perfect. It's the square root of, the derivative of this is 1 squared. 1 squared is 1. Got it. Next. Anybody? Okay. I was starting to do this before, but I think maybe we should have done it. Okay, I said however you want to do it, but okay. Let's do R prime, which is V of t. Okay? Do that first. What is that? I. Whoa. Where did you go? I. Next part. Anybody? Plus 2t to the 1/2 j plus, pretty easy, tk. All right. Now, I thought maybe that will help, because now what goes under here is the square of each of those. So 1 squared is 1. Got that one. Okay. Next. Plus, when you square this, the component of your j, obviously there's going to be a 4 here. And when you square t squared, what t to the 1/2, what do you get? Just t, right? The square of t, the square of the square root of t is t, right? All right. Now, and then the last one. T squared. All right. Now that almost produces for me a big boo hiss, because if that had just been a 2t in the middle, that would have been wonderful. But it's not a 2t in the middle, it's a 4t. Okay? So this is going to take a little more work to be able to integrate it. Okay? Now, here's the trick that they do here. Let's turn that around because it's a scalar quantity. That will be the same as 0 to 2, the square root of t squared plus 4t plus 1 dt. Now that was just rearranging the order inside the radical. Okay, let's complete the square of that. Okay, so that's going to be the integral from 0 to 2 of t squared plus 4t blank plus 1. It's all going to be under the radical dt. Now I tried to leave a little more room there, I just ran out of room. How do we complete the square of this? Yeah, divide the middle term by 2, that gives you a 2, and square it, and that gives you a 4, right? So go add 4 here. But we just messed that up, didn't we? Because now what we have to do is subtract 4 under here so nothing is changed, right? Remember that trick? Okay. So what does this give us? This is the integral from 0 to 2 of the square root of, this is now t plus 2 squared minus 3 dt. Now that doesn't look very promising, does it? And for the life of me, what you have to do is go to an integral table. I was trying to think if there's any quick way to do that. There's not. So I think your integral tables are at the back of the book in Appendix A, somewhere back here. And those who don't have them, your books at home or somewhere probably do, or invest it. Oh, here I have my page. I have page marking it. All right. What it is, it's a integral of a square root of a square plus a number. Okay. So in your integral tables here, you want a square root in the numerator, and that is your form that looks like number 16 in the back. That's the closest I can see so far. No. I believe 26 is the better one. Yep. That's 26. The square root of u squared plus or minus a squared. Well, your a must be square root of 3, and it's a minus there. Okay? So what we have here is your answer. Okay, copying down from 26, you got a 1/2, and then a big bracket, or parentheses. Okay, now they've got the u, and in our case the u is t plus 2. Okay. Times exactly what that square is, square root of t plus 2 squared minus 3. Okay. and then the minus goes here because it's a minus in our radical. A squared, which is 3, the log of absolute value, your u, which is t plus 2, plus exactly what's in the radical there, square root of t plus 2 minus 3. Okay, I'm running out of room fast. Okay. Now, and we're going to evaluate that from 0 to 2. That sounds like a lot of fun. So it's 1/2. I believe that 1/2 is strictly in front of the first part, times 4. 2 plus 2 is 4, times the square root of 4 squared minus 3. 16 minus 3 is 13. What a fun number. Minus, I think that's where I didn't hang on to my grouping symbols very well. No, it's the whole thing here. So 1/2 is in front of all this. Minus 3 times the log of 4 plus this thing I just did, root 13. Okay. All right. It's that thing minus, put a 0 in. So it's minus 1/2 of 2 times the square root of 1 minus 3 times the log of 2 plus 1, square root of 1, which is 1. Okay. So let's see what this becomes. I'm not liking this. So I'm going to pull the 1/2 out of all that. Okay, so it'd be 1/2 4 root 13 minus 3 log of 4 plus root 13 minus 2 minus 3 log 3. Okay. Surely it's got to be something nicer. No, it's not. Okay. So 1/2 of 4 root 13 is 2 root 13 minus 3/2 log of 4 plus root 13, close parentheses I left off, minus 1, half of 2 is 1, plus, wait, why is that? Because it's minus a minus, so that's a plus 3 halves log 3, which they say is around 4.816. Yay. Okay. There's your arc length. Now, if this hasn't convinced you on a relatively not that complicated of a problem, these integrals and the evaluation of the integrals can get really nasty really quickly. Okay? Arc lengths are like that. They have to have some really weird functions to come out anything that's easy to calculate. That's all doable, especially if you use a table like we did, but even then, it's a pain, a pretty big royal pain. but we did everything right. Okay, let's see how they did it. They may have some shortcuts here that might help us. Let's see. Okay. Use x of t equal t, yes. Y of t is 4/3, t to the 3/2, z of t is 1/2. This was the other way we could have done it. Then you do x prime is 1, y prime is 2, t to the 1/2, and z prime is just t. So when you do the arc length formula, it would be you put the square root of all those under there squared. That would be the integral from 0 to 2 of 1 plus 4t plus t squared dt. And that's just what we got. And that's what they did. They completed the square of the first two terms. They didn't show you how they did that, but that's what they did. And that's exactly what we got there too. And then you look that up in a table to get this is the integral of that, which is a joy. They left the 1/2 in all those, so that's fine too. Evaluate that from 0 to 2, and you get 2 root 13 minus 3/2 log of 4 plus root 13 minus 1 plus 3/2 root log 3, and they come up with about 4.816. And then they move on to something else, okay, before they do example 2. So let's go back and we'll do example 2. How are we doing time-wise? Okay, been going at it about an hour and a half, right? You need a break, or just going to keep going? Okay, I saw a thumbs up on the break. Okay, so let's take a quick one. Try to keep it less than 5 minutes. Okay. What is page 1 was the first test I gave in a class. We did all of chapter 11. We started 11:6. So 1 through 6 you don't have to do. Okay? Now if you want to do them just for funsies, you can. I'll give you bonus points if you want to do those. Okay? They're not required. But start with 7 through 10. And these are basically just identifying the quadratic surfaces. Now, I think what I've told you before, I hope I said it before, is you need to show all your work. Okay? On all 4 of these are so directly like the thing in the book. All you need to say is from the book or from wherever you're doing, what your standard is, similar to blah, 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 and then write down the name of the quadratic surface. Paraboloid, elliptica paraboloid, hyperbolic paraboloid, what are the others? Ellipsoid, whatever the name is, that's really all you have to write down there. Now, if you do the stuff at the top, 1 through 6, I need to see work on that. That's up to you whether you do them or not. It's not going to hurt you if you don't. There's not part of the test. But down here, just give the parent formula that is based on. Okay? That's all you have to do, and write the name. That's all the work you have to show. Now, the next part is the part on chapter 12, the part we're in now. Hopefully we'll finish it today. This, I need to see work. Now, you got more room to work on this one, and you got front and back. You can even use the back side of the previous page. So there's some room. If you need additional work, do it. But I don't remember if I said this to you or not, but let me say it again in case I didn't. If you just give me the answers, even if the answers are perfectly correct, the maximum you can get is a 50. Okay? A right answer will give you half credit, but you won't get full credit unless you show me your work. Like I say, there's 4 at the bottom of the first page. There's not much you can show there. Just show me that you've looked up something and you found it, and then write down the names. The next ones, those 10 there, that I'm going to need to see work. Okay? Does that make sense? And Write out as much as you need to using scratch paper, additional sheets of paper, front and back. Just identify where your work is so I can find it easily. Okay? Is that okay? All right. So you don't have to do the first 6 on the first page. That was just because I didn't have time to go and redo the test. So the last 4 on the first page and then the next 2 pages. All right. Now you can take your break. And we just finished example 1, and we're going to get started on example 2. All right. Find the length. Let me draw my line here. Find the length of one turn of the helix given by sorry, R of t is equal to b cosine t No, we didn't do this one, did we? No. We did something very similar to it in the last class, I think. B, or earlier, cosine t I plus b sine t j plus square root of 1 plus b squared, no, 1 minus b squared, tk. Okay? Find the length of one turn of the helix given by that expression. Now, there's a picture in the book. I appreciate them drawing it. It takes a while to, or at least it took me a while to see it really made sense. It didn't look like it did, but they're coloring in sort of the surface underneath the helix, and that sort of obscures part of the path. You're not doing the surface, you're only looking at the length. And I'm not sure why they drew the surface in except so you could see kind of what's going on. This indicates it's a circular there's a name for it, mapping onto the XY plane. That would be a circle. B cosine ti plus b sine tj. If you didn't have the k component, that would be a circle. You would get going around the circle. So it says one time around, that takes you from 0 to 2 pi, basically. Okay, one time around. Okay? Now, what this does for you, it takes you up the circle. Now, the radius is your b. That could be something less than 1 or greater than 1. They don't indicate here. It's just whatever your radius is. Okay. Now, the square root of 1 minus b squared, I'm sure that's going to come into play later. But I think you've got to assume from this b can't be greater than 1. B's got to be less than 1. Because if b was greater than 1, you have a negative in your radical there. And that just won't work. Okay? Now, there it is. So it's so bizarre they don't say that, but b has to be less than 1. There's just no way around it. Okay? That's why I thought it was going to be a plus there, but it's a minus. Okay. So, how do you begin? You want to find the arc length of one turn of that. How do you do it? How would you do it? Take a derivative, always a good try anyway. Okay, and what would that be? A little louder. Negative b sine t I plus b cosine t j square root of 1 minus b squared k. The t goes away because you're taking the derivative with respect to t. Okay? That's t to the first power, so it would just be the coefficient, which is that radical. All right. Now, what are we going to do with that? What are we going to do with that? It's also, you could call that the velocity function, if this were indeed a displacement. They don't say that. One turn of the helix. So yeah, you could say something moving around that one turn there. Okay? What do you do with it? Square root of the sum of the squares of the components. Okay? Make sense? In other words, the magnitude of this thing. The magnitude of this, which is the magnitude of this, which is what? The square root of? Help me. B squared sine squared theta, sine squared t, plus b squared cosine squared t, plus 1 minus b squared. Okay. Now, what do these two add to b? Oh, the sine squared plus cosine are 1. Factor out of b squared, you got b squared times 1, so this would be the square root of b squared. That's all those two give us. Plus 1 minus b squared. So that gives you the square root of 1, which is 1. Oh, okay. Now, one turn around, that's the magnitude of that r prime, is 1. Okay? So we're going to integrate one turn around, and that was from 0 to 2 pi. T going from 0 to 2 pi of dt. It's all that thing, dt. Well, that's just what? 2 pi. That's it. That's all, folks. 2 pi units. Okay? Now, this is if you're going around a helix whose radius is less than 1. No matter how much less than 1, it's going to, as long as that's your t, square root of 1 minus b squared t, if that's your k component. So if it's a great deal less than 1, like a very, very small number, that's going to be closer, this thing is going to be closer to 1. So it's going up faster. These things are really tight if b is very small. If b is closer to 1, then this is closer to 1, and this is almost 0. So it's going up very slowly, so you're almost just going around a circle. And then your radius would be 2 pi. If it's close to 1, the radius would be 2 pi. So that kind of makes sense. Okay. That was not nearly as bad as the last one. So let's now move to what they call the arc length parameter. All right. All right. Now, first do a definition of the arc length function. All right. Let C be a smooth curve. Again, no cusp, no angles, no sharp turns. C be a smooth curve given by R of t, defined on the closed interval a to b. And as long as t is something between the a and b, where it's defined there, then the arc length function is s of t. Okay, here's your s of t. This is some function of that. This is the integral. Now this looks very similar to what we did before. Very similar. In fact, let me go back and refresh your memory on how similar it is. It's this. S is equal to the integral from a to b of r prime of t dt. That's your arc length for any closed interval. The total arc length on there is S is equal to the integral from a to b of the magnitude of r prime of t dt. Okay? Fast forward here. Okay? Now, what you've done, this looks exactly the same, except you've lost your t's here and put your t up here. Okay? So basically what you've got now is a function of t as the arc length from a to some value less than b. This will be, as a function of that variable t, what that is. These are just dummy variables. You can put anything in here. You're integrating those out, and this will give you your what they call your arc length function as a function of your parameter t. Okay? And to do that is the same as before. This would then be the integral from a to t. T is your variable now. The square root of x prime of ut squared plus y prime of ut squared plus z prime of ut squared. Just the components of this squared, sum of those components, and take the square root. That arc length S is called the arc length parameter. Okay? This S is called the arc length parameter. This T was the parameter of your parametric equations. Okay? So that's sort of out of the picture. This is now what they call the arc length parameter. So, this is what it's trying to say. Let's say we had some curve, some R of t, that starts when t is equal to a, you're starting here, and then it does just wanders around here until it gets to t is equal to b. Your arc length parameter tells you how far you've gone when you've gone some time, you might say, between a and b. This gives you the function, what your arc length is at any time t between a and b, what the arc length is up to that point. When you get to b, then you go back and do the formula we showed before. Okay? But this gives you for any time t that you're going along that path. So the only difference is you substituted for parameter t from here, and that gives you S, which is your what they call the arc length parameter. It's a variable based on how far you've gone between A and B. Okay? Now, using the definition of arc length function, that's that definition, okay? And the second fundamental theorem of calculus, you can conclude that, okay? Now, this looks a lot like second fundamental theorem of calculus. And basically what that says, if this is your S, you can take a derivative of an integral, and your S of t would then be the magnitude of your R of t. Okay? And the S dt is exactly the magnitude of R prime. I said R of t, R prime of t. So in differential form, that says the ds is the magnitude of this times dt. So whatever your velocity function, if that's what you want to call it, first root of your displacement function, whatever you want to call that, your arc length, this is a measure. If you were to integrate this, this gives you how far along as you travel. Okay? Looks like a pretty simple concept. Maybe. Sort of. A little bit. Okay? In other words, this is your speed. So if you integrate your speed as a function of time, over time, you get how far you've gone. Okay? So yeah, that's just what we were saying before. Now here's example 3. Find the arc length function for a line. This should be pretty easy, right? Because what's the arc length of a line? The length of the line, okay? It should be pretty straightforward. So let's see if it is. Find the arc length function S of t for the line segment given by r of t is equal to 3 minus 3ti plus 4tj, as long as t is going from 0 to 1. So that's going to be some line segment. Then it says write r as a function of the parameter s. That sounds like it's a lot more fun. So let's see what we've got. T is going from 0 to 1. When t is equal to 0, you're at 3i 0j. Starting right here. Starting right there. 3i 0j. And then as t is increasing, going toward 1, when it gets to 1, it's 0i plus 4j. So you're up to here. So you're moving in this direction along that line. Okay? So let's write the arc length function S of t for that line segment. Okay? Reminding ourselves what that is then. Probably go back to this one. It's the integral from a to t of your, basically your speed square, your magnitude of your velocity function. Okay, so let's do it. One thing we got to do, guess what? Take a derivative. R prime of t is equal to what? Pretty easy. Second? Minus 3i, right? Yeah. Next? Plus 4j. Got it. Okay, now what we want to do is take the magnitude of that. The magnitude of this r prime is equal to the square root of 9 plus 16, right? Okay, which is square root of 25, which is 5. We always take the positive square root, okay? Now, doesn't matter what our t is, the t's have disappeared, that's 5, okay? Now, going back here again, your S of t, that's what we're looking for, the arc length function, is the integral from a, which was 0, to t of that 5 du, we'll say it, okay? So, the S of t is equal to the integral from a, which is 0, to t, which is something between 0 and 1, okay, of this thing, which is 5 du. We don't want a t there, put something else there. It doesn't matter what, just not an s, not a t, okay. So this will be 5u evaluated between 0 and t. And what would that be? Pretty easy. The bottom one will be 0. What will the top one be? 5t. You put the t in for the u. Okay? Substitute in for u. So there is your arc length parameter function, 5t, for this one. So if t is equal to 0, you're at 0 length. If t is equal to 0.1, you're at 0.5. If t is equal to 0.2, you're at 0.1. Okay, right, yeah, just 1, you know, at 1. So there's your length up to 1. When t is equal to 1, you're at 5. That's the total length of the function. Okay? So there's the arc length function is 5t. Okay? For the line segment given by blah, blah, blah. Write r as a function of the parameter s. So your r we want to rewrite that as a function of s rather than of t. Okay? All right. So let's rearrange this. S is equal to 5t, right? So let's solve this for t, have t is equal to s over 5. Does that make sense? No? Yes. Oh, okay, good. Okay, I thought you were shaking your head. No. Okay, so let's plug that in here. R now not a function of t, but of s, would be 3 minus 3 times 5 over s. That's what you're, no, I'm sorry, s over 5. I can't read my writing. Okay. S over 5 I plus 4s over 5 j. Okay? Write it again. R now as a function of s rather than a function of t is equal to 3 minus 3/5 s I plus 4/5 s j. Okay? Now, that's the second part here. I think that's all they want out of this problem. Okay? Oh, guess what you need to do here is put, since this is what you got here, you know t is going from 0 to 1. If s is 5t, so s is going from 0. When t is 0, s is 0. When t is 1, s is 5. Going from 0 to 5. Okay? So there's the interval for s. So 0 is less than or equal to s is less than or equal to 5. So it's just a scaling thing. Now, that was pretty straightforward. Maybe a little so what-ish, okay? What we're going to do now is observe something. What is the magnitude of this thing squared? I mean, the derivative of this. Let's do, we have what this is, 3i plus 4, minus 3i plus 4t, and its magnitude is 5. Let's see what happens to the magnitude of this. R prime of s. What is that? The 3 goes away. Derivative of 3 is 0. Derivative of this is minus 3/5 I plus 4/5 j. And what's this magnitude then? The square root of 9/25 plus 16/25. Is that what you said? And what is that? 1. Okay. Now here's the bizarre thing. The magnitude of your arc length. Take this back. When you write your R function, or your derivative of your R function, in terms of S, the arc length parameter, rather than in terms of T, the given parameter, your speed is always 1. Speed in the sense along your arc length parameter. Always equal to 1. Okay? This is, how is the arc length parameter changing per unit arc length? It's at a rate of 1. Okay? Always is. Okay. Now, this was a line, and it took a little bit of effort to do all this. Just imagine if this was any other curve. It could get nasty really, really quickly, and it does. Okay? Now, so for a smooth curve C, represented by R of S, where S is the arc length parameter, then your function, the length, which is a little bizarre, is the arc length as a function of the change of the rate of change of the arc length. Okay, so I don't even know if they call it S anymore. I notice they just write it down as length of arc would be the interval from A to B of your arc length parameter of your derivative of R with respect to the arc length parameter, ds now. Okay, now here's a little bit that really bugs me about this. We've just noted here that your limits here change. Here they were 0 to 1 for the t. There it is. For the t was 0 to 1. When you change it, it goes 0 to 5. Okay? Now, we were calling this A to B before, okay, for t. They're still calling A to B here, but now the A to B is the S, okay? And if you do this integration from A to B here, and the arc length parameter, this is 1, this will be S evaluated from A to B, and this will be B minus A. It's just merely the length of your interval, okay, which seems a bit odd, okay, the length of the interval, B minus A, because this speed along there with respect to S is 1. It's always 1. It's unitary. So however long your interval is, that's what you've got. All right. So I think we beat that to death now. Let's see how they did it. Okay, they're going to do the same thing. You take R prime of t, that was minus 3i plus 4j. Do the magnitude of that, we got 5. You do your arc length parameter formula, which is the integral of 5 du. Going from 5 to your to t, that would be 5t. Okay? Then writing R as a function of s rather than t, you have to solve that. Since s is equal to 5t, then t is equal to s over 5. You can rewrite R using the arc length parameter. With everywhere you saw a t before, you plug in this. It was minus 3/5 t. I'm sorry, minus 3t. Now it's minus, you plug s over 5 in for t, and you get 3/5 t plus, it was 4s, now it's 4/5 t. 4/5 j. 4/5 s, j. Now s is going from 0 to 5. So now we're down to the arc length parameter. The other theorem was arc length function, here's your arc length parameter. If C is a smooth curve given by R of S is equal to some x of Si plus y of Sj on a plane curve, or R of S is equal to x of Si plus y of Sj plus z of Sk, if you're in a space curve, where S is the arc length parameter, not any other parameter, arc length parameter, then always, always, always the first derivative of this with respect to S is 1. Okay? Meaning that the rate at which you're moving along the arc length relative to the arc length is 1. Okay. Moreover, if the rate at which you're moving along the curve relative to the arc length is 1. Moreover, if t is any parameter for the vector value function r, such that r prime of t, magnitude of that is 1, then t must be the arc length parameter. Okay? So if you ever run into that magnitude is 1, then you know that t is your arc length parameter, and you can rename it S. You'll seldom run into that. That's always true, but you might. Okay? Now, that was the theorem 12.7. And there's no problem that follows it. I thought there'd be an example. None. Well, I guess the one before it did it. So let's move on to the concept of curvature. An important use of arc length parameter is to find the curvature, the measure of how sharply a curve bends. For instance, in this figure, this is a plane figure here, the curve bends more sharply at P than it's bending at S. That's a very gradual bend here, really sharp bend here. Okay? So the curve bends more sharply at P than S. You can say that the curvature is greater at P than it is at Q. I can say S is Q. Okay? So this is a large curvature, that's a small curvature. Curvature at P is greater than the curvature at Q. You can calculate that curvature by calculating the magnitude of the rate of change of the unit tangent vector. There we have that again, capital T. It's a vector, so it's bold, with respect to the arc length S, as shown in this figure. Okay. Now, the figure just shows some tangents. Tangent here, tangent. Whoa! That's nowhere close to a tangent. That should be here. That drawing is pathetically poor. Is it true in your book? Yeah. If it's right here, that would be straight up. Over here, it's more like this. You see, this looks pretty good here, and this looks pretty good there. This does not look like a tangent vector at all. Okay? Lousy drawing. Sorry about that. The magnitude of the rate of change of t with respect to the arc length is the curvature of the curve. Okay? Now, this just shows how poor this is. If you had drawn this truly like this, you can see the rate of change from this tangent vector to that one. Huge rate of change. Big curvature. From here to here, very small rate of change, smaller curvature. You're getting closer to like it is at Q. But here there was a huge curvature. Their picture looks like the change here is actually less than the change there. It can't be. This curve needs to be tangential here. So that's a really, really lousy picture. As not shown in figure 1233. Sorry about that. All right. So the definition of curvature is, let C be a smooth curve in planar space. It doesn't matter which. Smooth meaning no cusps, no corners, anything like that. Nice, gentle, changing curve. Given by R of S, where S is the arc length parameter, which again is not an easy thing usually to calculate. The curvature K. Now this book does it differently from most books. Most books I've taught from have this as a kappa, the Greek letter K. This uses capital K. Doesn't matter what you call it. Okay? The capital K is the magnitude of the time rate of change of the unit tangent vector with respect to the arc length parameter, which is T prime as a function of S. The magnitude of that. How rapidly is that unit tangent vector changing as S is changing per unit S? And when it's a sharp curve, boy, that's changing big time. When it's a gradual term, it's changing incredibly slowly. So it'll be a small thing. A circle that has the same curvature at any point. There is some circle that has that same curvature at any point. Moreover, the curvature and the radius of that circle are inversely related to each other. That is, a circle with a large radius has a very small curvature, and a circle with a small radius has a very large curvature. Okay? And here comes example 4. Goodness, I'm running out of steam. Show that the curvature of a circle of radius r is the capital K curvature is 1 over r. Okay? So, what is the circle of radius r would be, and this is in a plane, so we'll say x squared over r squared plus y squared over r squared is equal to 1. Now that's one way to express the equation of a circle of radius r. They're actually going to do it this way. That's one way, but maybe that would be harder to do, so let's erase that and do it their way. Okay? Okay. R of theta, going to make a parameter of theta. This is not necessarily S. In fact, will definitely not be S. Is equal to R cosine theta I plus R. Wait, these are not vectors here, these are scalars. This is the radius, the magnitude of the radius. Sine theta J. Okay? There's your R function as a function of the angle R. Okay? And we know that, don't we? Because if this was a radius 1, cosine theta I plus sine theta J would trace out a circle. Exactly. Unit circle. Now you have a circle of radius R. Not a unit circle, but radius R. Okay. Now, what would we do with that? They're doing a tricky thing for us here. I don't know if you remember, okay, from trig class, that the arc length is equal to r theta. Remember that? Sort of. That's with one huge caveat. Theta has to be measured in radians. Don't ever try to use that formula with theta in degrees. Okay? Now this comes directly from something that I hope you do remember. The definition of a radian is S over R. Remember that? Okay. Let's do a circle here. Any size circle. Okay? of radius r. If you see if I can draw. I can't draw circles very well, but let me see if I can. Okay. Supposedly that's a circle. That's not a very good looking circle. That's still not very good looking, but better than the other one. Okay. Now here's your radius right here, right? There's your radius. Now let's do that length, but bend it along the circle. Does that look about right? Relatively close? So let's do this. This is R, and this S is equal to R. Okay? Then this angle right here is 1 radian. This theta here is equal to 1. And if you remember, this is calling on memory again. What is 1 trip around the circle? Okay, that's degrees. How many radians? 2 pi radians. So 2 pi radians is the angle around the circle, and your circumference is 2 pi r, right? Always. So if using this formula here, 2 pi r is equal to r times 2 pi. 1 trip around is going to do that. Yeah, it has to be true. It will not work for degrees, okay? So with that being the case, S is equal to r theta. That means theta is equal to S over r. So let's now rewrite this r as a function of S, and that would be r times the cosine of S over r I plus r times the sine of S over r j. Okay, you just plugged in that substitution. My eyes are driving me nuts. I think it's staring at the light so long. And it may do a little bit of strobing, and I just shouldn't be rubbing them because of the drops in this one. Okay. So now we're ready to take our derivative, right? R prime of S is equal to what? This is taking it with respect to R. I mean, with respect to S, sorry. Be R, it's going to be a minus sine of S over R. Okay, but wait, you got a chain rule thing there, taken with respect to S times 1 over R, right? Chain rule here. Derivative of S over R with respect to S, that's the same as derivative of 1 over R S with respect to S. Well, that's 1 over R. R is being a constant, S is your variable. That would be your 1 over R. So derivative of this is 1 over R. So that goes here too. Okay? And then, like you were saying, go on, plus R cosine theta of S, not theta, S over R. Goodness gracious. Theta is S over R then times the derivative of that is again 1 over r. Okay, so what we've got here is minus sine s over r plus cosine s over r. Okay, that's your r prime. Take the magnitude of that, and you have square root of sine squared s over r plus cosine squared s over r. And guess what that's equal to? 1. So sure enough, this is your arc length parameter. Okay? That thing right there, you just shown the magnitude of it is 1. The magnitude is 1. That is your arc length parameter. S is equal to r theta. Okay. Now, forgot where we were heading here. Let's go back here. What's that? Really?
Yeah, they were locking the door.
Oh, they were. I'm sorry, I didn't know that. Y'all should have told me. Just now?
Yeah, I think I did.
Huh?
I think we did.
Oh yeah, you can get out. Oh, someone came and locked the door. I thought someone was locked out. Oh, okay, good. Seems like they would look in the window to see, but now if you do go to the restroom, don't close the door all the way, okay? Because we'll have to let you in there, which we will, I guess. Okay. All right. Okay. All right. So we got this far here. Now we have to go back from here to our unit tangent vector. And I don't know that I want to scroll back that far. Let me refer you to the unit tangent vector, which would have been back in the beginning of 12.4. Okay? Here's what our definition for unit tangent vector was. That's on page 845 if you got a text. The unit tangent vector as a function of some variable parameter, I'll put t down, is equal to r prime as a function of that t divided by the magnitude of r prime as a function of that t. Okay? That is your definition of the unit tangent vector. Okay? Now, what we have here is r prime as a function of s, and that's I can't believe it, but I left off my unit vectors here. There's an I here and a J here. Okay? And this was the I here and a J here. Okay. And then when we took the derivatives, we did away with the I's and J's. Sorry, I left that out completely. Okay? So this would then be, it's going to be of S, not T, but it still should work. The unit tangent vector would be just simply r prime of S. Okay? Because when you divide by the magnitude, that's 1. So this would be minus sine of S over R I plus cosine S over R J. Okay? Now, that's your unit tangent vector. Okay. Now I'm going to go back one slide and see that kappa is the, you got to take the derivative of that unit tangent vector with respect to s and then take its magnitude. Okay, so that's the last step. I said kappa again. Capital K is what they're calling it in this one. Okay, so again, the capital K was the magnitude, no, it's the magnitude of the first derivative of the unit tangent vector. So the magnitude of the first derivative, okay, now this is where I run into problems. It's no longer a unit vector when you take its derivative, so, okay. So we've got to do that. So first thing we've got to do is find the first derivative of that. So here is the unit tangent vector here. Let's take its derivative. What do we get? Here is the unit tangent vector right here. Okay? We want its first derivative. Its derivative. It's what? Negative cosine S over R over R, right? Chain rule again. I don't have enough room. Minus sine S over R J. Okay? Now, what we want to do now is take the magnitude of that. Okay? And how in the world does that R come up looking like a 5? I do not know. I do not know how that happened. I said R and it looks like a 5. Okay. Okay? So now we need to do that. So the magnitude of that, I can't write, first derivative of the unit tangent vector with respect to S is the square root of, when you square this, you get cosine squared S over R squared, right? Plus, because when you square it, minus times minus is plus, sine squared of S over R squared. Okay? But what do those numerators add to? 1. So you get the square root of 1 over R squared, which is what? 1 over R. You've just proved what they asked you to. It says show that the curvature, capital K, of a circle of radius R is 1 over R, and there it is. Okay? Now, let's clear some of my writing out of the way, all of my writing out of the way, and let's see how they do it. Without loss of generality, we can consider the circle to be centered at the origin. Why not? Okay? Let xy be any point on the circle, and let S be the length of the arc from R0 to xy. From here to there, that's your length R, not length S. Okay? Now, right, okay? By letting theta be the central angle of the circle, you can represent the circle by R of theta is equal R cosine theta I plus R sine theta J. That's, yeah, where theta is your parameter. Okay? Using the formula from the length of a circular arc, S is equal to R theta, that's as long as that theta is measured in radians, you can rewrite R as a function of theta in terms of the arc length parameter, which is your S. Okay? So basically you take this here and solve this for theta, and that gives you S over R. So now everywhere you see a theta, you put S over R, S over R. And that formula up there. Okay? There's your R of S. Okay? Now, take a derivative of that. R prime would be okay. Here you had R in front, and then when you take the derivative in the chain rule, you have a 1 over R. That wipes out your R's. Okay? So that's why they left them off here. Minus sine S over Ri plus cosine S over Rj. Okay? Because the R that you had in front here is divided out by the 1 over R here, the same here. It follows that when you do check that, your magnitude there is this thing squared plus that thing squared, and that's exactly 1. Okay? Which implies that this unit tangent vector is that R prime. This is your arc length parameter divided by 1. This is 1 R prime. Okay? And this would be, this is it right here. R prime is this divided by 1, and that's your unit tangent vector. Minus sine S over Ri plus cosine S over Rj. Okay? Next thing we're going to do is take a derivative of that. Okay? The derivative of that is minus cosine S over R times 1 over R minus 1 over R times the sine of S over Rj. Take the derivative of the magnitude of this, and this would be cosine squared S over R squared plus sine squared S over R times 1 over R squared, or over R squared, and the square root of that, the numerators, the squares go to 1, the denominator is R squared, square root of R squared, 1 over R. Okay? At every point on the circle. So yes, the curvature of a circle is the inverse of the radius. Okay? Always. Okay? Now, that then leads to the formula for curvature. How are we doing on time? Yeah, we got time to do this one. If C is a smooth curve given by R of t, any smooth curve R of t, then the curvature K of C at any point t is the magnitude of its first root of the unit tangent vector divided by the magnitude of the R of the velocity of R of the R prime of t. Now, there's a formula. Okay, now we might need to refresh our memory how they got that. Let's go back a little bit. It's T. Here it is, right here. T of S is R prime of S over the magnitude of R prime of S. The first derivative of T of S, that's going to be your curvature. Now this is of S. We probably shouldn't be using S here. Let's go back again. It's probably not in this section. Sorry, I forgot. It's in the previous section, so I can't go back to it. Okay? Oh, that was the previous. Okay, here it is. Okay. Well, actually, curvature was here, so yeah, but curvature was only defined in terms of ds, okay, not dt, okay? So then you'd have to go back to your S and do it, and they've skipped too many steps here. So it's probably not going to be right. Just take their word for it. This is how it's defined. Is first derivative, the magnitude of the first derivative of the unit tangent vector divided by the magnitude of the what you might call the velocity, first derivative of the displacement vector. Okay. Now think about what it's doing there. The rate of change of the unit tangent vector, that certainly has something to do with curvature, and divide that by the rate of change of your derivative, rate of change of your function, and that gives you exactly your curvature. Okay, this is how they're related. Now, going back again, if you remember, the rate of change of unit tangent vector was your magnitude of your velocity vector cross the acceleration vector. I don't know if you remember that, but we were using that at the end of the last class. Okay? Divided by r prime of t. No, not quite right. Well, this jumping over sections sort of drives you crazy. That's not right. Oh, no, that's unit tangent vector. Ah, here it is. Okay. Well, it's not worth going. Yeah, what is worth? When we have those shortened equations, there it is. I missed. Nope. All right. It's not intuitively obvious here, okay? But anyway, this is the magnitude of this cross product, okay? Now, divided by the magnitude squared would be this, and then you have another one, so that gives you the magnitude of that cube. Okay. Now, this thing right here, this denominator here, is ds dt, if you remember from that. Because that's true, the first formula, that's this one, implies that the curvature is the ratio of the rate of change of the unit tangent vector to the rate of change of the arc length. So you could write this as unit change, the rate of change of this, and that's the magnitude, to the rate of change of arc length, which is exactly this. Okay. To see that this is reasonable, let delta t be a small number, then as what this is, this over that would be approximately. Okay. Here's the t of t plus delta t minus t of t divided by delta t. Okay? Oh, that's what this is. And this is s of t plus delta t minus s of t divided by delta t. Okay? This is this vector equation, that's a scalar equation. Okay? And this is what it's approximately equal to. And your delta t's you can think of as going out here. And so you're just left with the change of this over the change of that, which is exactly what, pretty close to what this is saying, okay? It's delta t over delta s. There must be more on the next slide because that's not making that much sense the way it is. That seems to have nothing to do with this. So in other words, okay, for a given delta s, change of arc length, the greater the length change of your unit tangent vector, the delta t, the greater is the curvature, okay? So if you're going from here to here, and that's a fixed delta s, your unit tangent vector, and again, they've drawn a really, really lousy unit. Oh, no. Okay, I see what they've done. This is this vector. This is that vector. So your delta t is, not too bad. Okay? Now, for this delta s, so the delta t over delta s is fairly small. But if you go down here, now see what they were trying to do before. Okay? Here's your unit tangent vector here. Here's the unit tangent vector there. Look at the difference of that one. The delta t is like this for the same delta s here. And so this is going to be huge compared to something smaller. This is something small compared to something much bigger. So this is a small curvature. This is a really large curvature. Same curve, but it's different portions of the curve. Okay? So that's what these figures are trying to illustrate. Finally, they got around to doing it. Now, let me go back to that one that I said they messed up the picture on and see if I can figure out why they did it wrong. There was the one I was looking for. Okay, sorry about that. Okay. No, they just messed it up. I mean, there's no way to rectify that. That was just screwed up. All right, that's what we just finished. So here's example 5. Do we have time for it? I think so. Let's try it anyway. Find the curvature of a space curve. Find the curvature of the curve given by 2ti plus t squared j minus 1/3 t cubed k. Okay? Now, what we're going to use is this formula. Okay? Oh, I'm sorry, this formula. Because we don't necessarily know what this one. So take this back. All right, this formula. That's a relatively easy one to deal with. Notice the term relatively. Okay. So what are we going to need to know first? Our prime of t, our double prime of t, and then we're going to need some magnitudes. Right? Okay. So, and a cross product and then the magnitudes. So what do we do first? Take a derivative, always a good answer. Okay? And what would that be? 2i plus 2tj, say again, minus t squared k. Very good. Now at some point we're going to need that magnitude. Do you want to do that there or wait till later? Okay, take the derivative next. R double prime of t, we're going to need that too. And what's that going to be? 2j, is that what you said? Okay. K. All right. Now, there's two things you got to do. You got to take the cross product of those two, three things. Cross product of those two, then you got to take the magnitude of that cross product, and you've also got to take the magnitude of the r prime. Right? Okay. Which you want to do first? Magnitude of r prime. So r prime of t magnitude. What would that be? Magnitude is going to be a square root. 4t squared. Second? T to the fourth. Got it. Okay? Now, another thing we've got to do is the cross product of those two. So r prime of t crossed r double prime of t. Now remember how we do that? I, j, k, these should be carrots, tops, I, j. I'm going to make it like it's determinant, though writing 5 of them doesn't make it a determinant. But what do you put next? Component of R, 2t minus t squared, and then repeat the first two, 2 and 2t. And then the last one would be 0, 2, minus 2t, 0, 2. Okay? To do the cross product, we go down like this. Okay? That's going to be a minus 4t squared I. That's going to give us a 0. That's going to give us a plus 4. Let me leave a little room there. Plus 4k. You okay with that? Now let's do the up products, which are going to negate these. That one's going to be 0, right? This is going to be the minus of that. Well, it has a minus in it already, so that's going to be plus 2t squared I, right? And this is going to be, that's got a minus, so it's going to be a plus 4t j. Combine those together, and you get a minus 2t squared I plus 4t j plus 4k. Right? Now what do we do with that? A magnitude. Okay? So we do the magnitude of this, which is going to be, magnitudes are square roots, and what do we have? 4t, I can't write, 4t to the 4th plus 16t squared plus 16. All right? And our curvature, that's what we're looking for, capital K curvature, is equal to the ratio of this thing, the cross product, magnitude of the cross product, the square root of 4t to the 4th plus 16t squared plus 16 to this thing cubed, right? So that's going to be 4 plus 4t squared plus t to the 4th times the square root. Well, yeah, let's do it that way. 4 plus 4t squared plus t to the 4th. Now, I don't know if that's the best way to write it, but that's written. Okay? Now, wait a minute. Did I forget something? No, they forgot something. Oh, no. Sorry. They did it a different way. Sorry about that. Okay? They did it the first way, not the second way. It sure should come out closer than what we're seeing here. All right. There is something we can do to this numerator, which is factor out a 4, which is square root of 4 is 2, and that leaves us with a t to the 4th plus 4t squared plus 4 over, that's going to exactly wipe that out, isn't it? Okay? leaving us 4 plus 4t squared plus t to the fourth. Am I crazy, or is that not true? And then they note that that's the same as 2 over 2 plus t squared squared. Yeah, and that's our curvature. Okay. I wasn't looking far enough down the page yet. We got the same thing they did. T squared plus 2 squared. Yeah, 2 over t squared plus 2 squared. Just want to say, I think I've lost my mind here. All right, we're awfully close to being out of time, aren't we? Okay, let me find my pencil. There it is. Okay, we'll start next time with the top of page 860. Now, the book did it one way, we did it the other way. We came out with the same answer. Okay? Let's see what homework problems we're ready for now. Ooh, this is a long section, isn't it? Okay? Any of the odds, 3 through 7, they're all at Calc Chat. 9 should be at Calc Chat. Any of the odds 11 through 15, they're at Calc Chat. 13's at Calc View. Do 17, it's at Calc Chat. And do any of the odds 19 or either 19 or 21, they're both at Calc Chat. 21's at Calc View. I think you can also do any of the odds 23 to 27, they're all at Calc Chat. And perhaps into 29 through 35, they're all at Calc Chat. And maybe even 37 or 39, they're both at Calc Chat. And let's stop for a moment there. Yeah, and we'll pick up the rest of those later. Now, we did not finish chapter 12, but I already gave you the test for it. What that means is the test will not be due. We'll finish this on Monday, meaning you'll have a week from Monday. So you basically have a free weekend working on it. Now, you got the test, right? Everybody, okay? So you can do 7 through 10 on that first page, because that was a long time ago. And I think you can do everything think you can probably do everything 1 through 9. You don't have to do them all, but you can do 1 through 9. 10, you might want to wait and see, but I think we've done everything in 10 too. So I believe you can do all those, but you don't have to, okay? You've got a week and a half to work on this, okay? So don't sweat it yet, all right? We'll finish 12.5 next time, and I'll pass out the test to anyone who wasn't here, and they'll have a full week. And you can take more than a week. Let me tell you about that too. All that you have to do is make sure you get it back into me before we finish chapter 13. And 13 is a long chapter, okay? So don't sweat it. You're going to have plenty of time to work on the test I gave you today, okay? You got at least 2 weekends and longer if you need it. Good deal. Any questions? All right. That's it then for today. Move on from there.